specific heat and energy transfer. So we've talked a little bit about the meaning of temperature. And again, temperature is related to the kinetic energy of the atoms or molecules that make up a material. It's how much those particles are moving around. Now, heat is when you transfer energy from one object to another object. And a heat transfer leads to a change in that object's energy. So heat is energy transfer, and we use the symbol Q to represent the amount of energy transferred by heat. And when an energy transfer occurs, that changes an object's internal energy. We use the symbol U for internal energy. That's the cat. And internal energy is a combination of the internal kinetic energy of an object, its temperature, with the internal potential energy of the object. That's the bonding energy between atoms, and the chemical energy keeping atoms arranged in a certain configuration or arranged in certain molecules. So this internal energy consists of kinetic energy, namely temperature, and potential energy. That's related to the forces between the atoms, maybe chemical bonding. So heat transfer leads to a change in internal energy. It could be an increase in internal energy. If an object's getting heat added to it, it would be a decrease in internal energy if an object's losing heat. Now, when an energy transfer occurs, the amount that this kinetic energy changes, or the amount that the temperature changes, is related to an object's specific heat. So this quantity of specific heat that we'll learn about is related to how difficult it is to change an object's temperature. And here's how it's defined. Specific heat is defined as that heat transfer divided by an object's mass times its change in temperature. So it's related to the object's change in kinetic energy. It's like the heat added divided by a quantity proportional to the change in internal kinetic energy of the object. And a lot of times we turn this equation around a little bit to write heat equals mc delta T. That's where specific heat becomes really useful in telling you the amount of heat energy that's involved in a temperature change. Now, the specific heat value depends on the material. So some materials have larger values of specific heat than others. That means objects or materials with large specific heat values don't change their temperature very much in response to heat transfer. The classic example of this is water. Water has a very large specific heat. You have to add a lot of heat energy to it for its temperature to change in any significant way. That's why it takes a long time to boil a pot of water on the stove. Most metals, on the other hand, have pretty small specific heats, and their temperature changes quite rapidly when you add heat to them. So water takes a lot of time and energy to heat up or cool down. Metals heat up and cool down very easily and rapidly. Your textbook has a table of specific heat values for all kinds of different materials. And I'll do two examples here involving water and one also involving iron. So first example, how much heat, how much energy must be added to raise the temperature of 1 kilogram of water from 20 degrees to 100 degrees Celsius? So 20 degrees is about room temperature, 100 degrees is boiling. So how much heat energy do you need to boil 1 kilogram of water? Maybe a bowl of water. Well, we just use this equation directly. mc delta T, the mass is 1 kilogram. The specific heat value for water, according to the table in our book, is 4186 joules per kilogram per degree C. And then you multiply it by the change in temperature, temperature final minus temperature initial. And that gives us 334,880 joules of heat. It's a significant amount of heat. It takes a while to boil that water. Now let's look at maybe a more dramatic example. In this example, let's consider a process that a blacksmith, a metal worker, would do when they are finishing with working with iron. So typically, as a last step, after you've shaped your iron at a high temperature into the shape you want, is to plunge that iron into a bucket of cold water so that it cools down very rapidly and freezes in the microstructure, the atomic arrangement of iron atoms, so it'll be stronger. That process is called quenching. So let's say that a blacksmith takes a 1 kilogram iron horseshoe and quenches it in a bucket of water. And that horseshoe is red hot to begin with. Red hot for iron is about 700 degrees Celsius. Let's say this bucket of water is 20 kilograms of water, so a decent sized bucket, and that water is at room temperature, 20 degrees. After the iron and the water come to thermal equilibrium, what's the final temperature? So in this process, we have one object that's very hot, it's at a higher temperature, that's the iron. And we have an object that's much colder, the water. And so the hot object gives some of its internal energy to the cold object. And that energy exchange, that heat exchange, continues until the system reaches thermal equilibrium and both objects are at the same temperature. So mathematically, we write this process as follows. The heat absorbed by the cold object is the heat donated by the hot object. That's really just another expression of the law of conservation of energy. The energy from the hot object goes to the cold object. This is a closed system. The energy is not going anywhere else into the environment. It's just these two things. So the energy from the hot iron horseshoe is going into the cold water, and it'll heat up that water. Let's see how much it gets heated up. So this water, let's say, I'm going to use label 1 for the water. M1C1 times the change in temperature for the water. So the change in temperature is T final for the system minus the initial temperature of the water. Okay, mass of water, specific heat of water, final temperature of the whole system of the bucket of water plus the iron, minus initial temperature of the water. It's just this equation. And that equals minus the same thing for the lead, or for the iron, I mean. Horseshoe's made of iron. M2C2, that's for the horseshoe. T final minus the initial temperature of that horseshoe, which I'll label T2. Now our goal here is to solve for the final temperature of the system. So there's some algebra that needs to happen. I'll do this real quick. You can double check this at home. Here's the result. And by the way, this is true for any situation where you have two objects at different temperatures. You put them together, this is the final temperature. So I wanted to solve it for the general case. In this case, 1 refers to the water, 2 refers to the iron, and note that C1 for water is 4186 joules per kilogram per degree C, and C2 for iron is 448, the same units. And when you plug in all those values, you get this kind of surprising result that the final temperature is 23.6 degrees. So 20 kilograms of water is just kind of a normal sized bucket, maybe like that. And this horseshoe is red hot, 700 degrees C. But because water has such a large specific heat, almost 10 times as big as iron specific heat, it's able to absorb all of that heat energy without its temperature changing very much. So that by the time the system comes to thermal equilibrium, the overall temperature is only changed by a few degrees. So water is really good at absorbing heat. That's why if your car overheats, you can use water in place of coolant, and that'll get the job done for a while until you can find some real coolant. The water is able to absorb all that heat from your engine to keep your car at a relatively constant temperature. And this is also responsible for environmental phenomena, like why the weather is more consistent and more mild closer to the beach than inland, because the ocean is a giant reservoir of water, and it's able to absorb heat energy from the sun without the temperature changing very much. In contrast to the desert, it's a bunch of rocks that are mainly made of metals, so when they absorb sunlight, their temperature changes very rapidly.